Hello everybody, and welcome back to my second episode of Leesie's Astronomy Crash Course. Today we're going to be talking about the only star in our solar system, our Sun. And this video will be a general overview of our present Sun, not necessarily its life cycle. I'll get to that in a later video. But several of you requested me to go with the timeline that I proposed on one of my posts, if you saw that. So we're going to go into the Sun. And I made a cool little infographic. So here we go. This is our Sun, and I labeled it Sun. And this isn't everything about it, but here's a small overview of some important terminology and a little visual representation I'll be referencing throughout this video about things on the Sun we should pay attention to and look at closely. So we can see here, I broke this down into layers of the Sun. So inside we have a core. And then the two most important regions are the radiative zone here, and then the convection zone up here. And then further on, we have these areas of flow, and then we have the photosphere up above, and I labeled them here. And then we also have this area in here, which is like, can't really see it. I didn't mention it, but it's between the radiative and convective zones, and that is called the tachocline or tachocline. I've never really heard it pronounced properly. And then we have subsurface flows and the photosphere, which comparatively are very, very thin. And I mean, like, they're thin in density. They're not actually very thin in thickness, but in density they're very thin. And then we have several things along the surface in the chromosphere and photosphere, which I'll get into later. And those include sunspots and prominences, flares, the coronal holes, filaments, spicules, floculae, coronal mass ejections, ERFs, all that, Lemmon bombs. We'll get into all that. But here is a little picture that you can go back and reference. And this is the corona, which extends all the way out. So here it is. And so let's start with giving a little bit of information about our star. So it is actually 1.39 million kilometers in diameter, so it's the biggest object in our solar system. It actually holds about 99.8% all the mass in the solar system. The other 0.002% is Jupiter, actually, or about 0.02%. All the rest of the mass is just super tiny. It's minute. It doesn't really compare at all. And okay, also it is 4.5 billion years in age. So it's as old as the solar system itself. It formed with the solar system in this thing called a planetary disk, or a protoplanetary disk, and it was called a protostar when it was first formed, but we'll get into stellar formation and all that later. And from Earth, it's a coincidence that both the moon, which orbits several 100,000 kilometers out, and our sun both appear half a degree in the sky. And your fist is about 10 degrees in the sky, so if you stack your fists up, you can see. So it's about, like, I would say, like half your finger is about the sun and the moon. So it's about half a degree in the sky, which is why eclipses, we can get total eclipses, which is where it's like if I'm the Earth and you're the sun, then the moon passes in front and blocks it all out like this. So then you can just see the corona on the outside. This is not a very structured video, but I'm trying my best. So that's some facts and information. It's also I believe, 150 million kilometers from Earth. So it's pretty far out. We call that distance 1 astronomical unit, or 1 AU. So if you ever see anything mentioned in AU, it's just the distance between Earth and the Sun, or 150 million kilometers. On average, we actually have a 3% elliptical orbit, so it varies ever so slightly, but not by much. I think it's about 3 million kilometers that it varies, so it's not a big variation. And we'll go into a bit more about that when I talk about Earth in the terrestrial planets video, but that is not the reason for the seasons. The tilt of Earth, which is 23.5 degrees, is the reason for the seasons. So anyway, as you can see in my little infographic, we can see that the Sun has layers, just like Earth does, and it actually has like 7 layers, sort of. I'll get into why. There are some layers that kind of blend into others and don't really seem to be their own thing, per se. But at the core, we have the core, such an original name, and it's the hottest part of the Sun. And this is where most of the fusion happens, because it is so hot that it's able to hold fusion, which is basically fusing hydrogen gas into helium gas at a rate of 700 million tons into 695 million tons per second. And that extra 5 million tons of mass is converted using the Einstein's equation, E equals mc squared, into energy. And that energy is what is used to power the Sun in simplistic terms. So that 5 million tons of mass is what is used to power the star. And the energy produced by this fusion kind of radiates out through the star in multiple different layers over long periods of time. So a common misconception is that the Sun will fuse things and immediately burst it out, like instantaneously, but it actually takes many thousands of years to radiate out properly. So I'll get into why and how this happens. But the temperature in the core is about 15 million Kelvin. It is hot. It is super boiling hot, and it's not even something we can really think about, but that is like excessively hot. And the density is 150 grams per centimeter cubed, which is about 8 times the density of gold, which is 19.3 grams per centimeter cubed, and it's 13 times the density of lead. And I believe lead is 11.3 grams or 11 grams per centimeter cubed. So it is very dense in there. It's so dense, in fact, that gas doesn't really stay in a gas form. It creates this thing called plasma. And plasma is basically where you have your atoms and their electrons going around the nucleus of those atoms. And it's so hot that basically those electrons kind of break free of the atoms, and it creates this charged soup. Because if we get any type of moving electric flow, we get a magnetic field. So that's important for later. But basically the whole core is just plasma. Most of the Sun is just plasma, essentially. It's all plasma. Because it's so hot and so massive, it can make plasma. And so, yeah, it's about 138,000 kilometers thick. And I don't remember every statistic. I remember a lot, but I don't remember everything, so I'm referencing some notes. And that's pretty thick. However, it is 1.39 million kilometers in diameter, so it's not too thick. The core is actually not huge. It is about 25% of the Sun's radius, though. Not the diameter, but the radius. And it releases gamma rays and these things called neutrinos, which I'll talk about later. But gamma rays are basically the most intense type of wave or radiation. And actually the Hulk roller coaster uses some gamma rays, which is super cool. And then that energy from the core travels outwards in the form of radiation to this thing called, you guessed it, the radiative zone. We're so creative in astronomy with our names. But the radiative zone is about 300,000 kilometers thick, so it's double, basically, the thickness of the core. So it's about 2 times as thick. And the density is much less here. It's about 0.2 to about 20 grams per centimeter cubed compared to 150, so it's definitely lighter. And the energy moves outward via radiation over periods of like 100,000 to 170,000 years. So it takes like a long time for that energy to reach the outer edges of the radiative zone. And basically it moves around through photons. And we'll learn about photons, but photons are basically like light particles, is the simplest way I can explain them. And they move in random directions, and they kind of bounce into each other and then bounce and bounce again over thousands of years until they reach the outer sections of the radiative zone. And the temperature is about 7 million to 2 million Kelvin, so it's definitely cooler than the 15 million Kelvin in the core, but still boiling hot. Boiling hot. Okay, and then after it goes outwards from the radiative zone, it reaches a thing called the convection zone. Again, a really, really original name. It's basically just a zone of convection, like we have here on Earth, or in like hurricanes, or like Santa Ana's, all convection basically. The temperature is about 2 million Kelvin, so still very hot, and it's about 200,000 kilometers thick. So it's not as thick as the radiative zone, but it's definitely thicker than the core. And the density is like 0.0002 to about 0.2 grams per centimeter cubed, I think. So it's definitely thinner. And that heat kind of circles. So as I can show you in the infographic, in the convection zone, as that heat is radiated out, it kind of circulates. And the plasma that is hotter rises and cooler plasma falls. And remember, moving charged particles like electrons that have a they have a negative, oh my gosh, at least they have a negative charge. So that moving charge creates a magnetic field, which is super important, and I'll talk about that in a bit, but hang on to that thought. So the hot plasma rises and the cool plasma falls and creates these convection cells. We actually call those granules, and the bigger ones that are like 30,000 kilometers thick are called supergranules because, again, we're super original. So that's the most important thing. And then afterwards, we reach kind of like the point where we're no longer really at a surface or in the atmosphere of the sun. The sun doesn't really have an atmosphere. It's kind of hard to differentiate that, but we generally say we've reached the atmospheric layers of the sun when we transition from the convection zone to a thing called the photosphere. And the photosphere is literally called the light sphere. That's the translation of the photosphere, because photo is light, so light sphere. And the reason that we call it this is because it emits the majority of the visible light that we see on Earth. It takes 8 minutes for light to travel from the sun to the Earth, which at the speed of light, it's like, that's the fastest thing in the universe, and it takes 8 whole minutes. And it just tells you how far away 150 million kilometers is. It's a long way. And so that's the first layer of what we call like the solar atmosphere. And it's only 402, you can say 400 kilometers thick, so it's not very thick at all. But the temperature is still 5,500 Kelvin. So it's still really, really hot, and that's enough to boil away carbon and diamond, anything else that you're like, let's just chuck this at the sun, it will boil that. It will boil it up right away. And most of the sun's radiation that's been churning through like the core to the radiative zone, to the convection zone, is now radiating away into space from here. So the photosphere is kind of the region that happens. And it does have kind of like, how would I call it? Like, a carpet that kind of is textured and fluffy. It looks like a granular kind of appearance, or like maybe, what do you call that, porridge? like it looks like porridge. Like it's like a little fluffy granular appearance. It has that appearance in the photosphere. And here we can see different phenomena like sunspots and flaculae and filigree. And filigree is basically like the granular appearance that you see. And sunspots and faculae we'll talk about later. And then after you reach the photosphere and you travel upwards, you go from about like 2 times 10 to the negative 7 grams per cubic centimeter up to like 10 to the negative 10, 2 times 10 to the negative 10 grams per cubic centimeter. So it gets like a lot thinner. And the chromosphere is like 400 to 2100 kilometers above the photosphere, but the temperature gets hotter. And this is so weird because you're thinking like it's farther from the core, so that means that it should be cooler because it's not close to that 15 million degrees Kelvin. That's so odd. And we actually don't know why this is, and it's called the coronal heating problem. And we're still trying to figure this out, why this happens. There are some people that think it could be due to something called the magnetosphere, which I've been poking at, and I'll get into more detail later. But that could be a reason that we have this coronal heating problem, but we don't really know. It's not quite sure. So if you are interested in researching that topic of interest, you should go for it. Yeah. And so in the chromosphere, we have things called spicules and Ellerman bombs, which again, I'll get into all the types later. The sun isn't my area of expertise. I'm very interested in radio astronomy and nebulae and stars and galaxies. And the sun and the planets aren't really my area of expertise, so I have to look down at my notes sometimes because I don't remember everything. But I'm trying. I'm trying my best. And then we go to this thing that scientists don't really know if it exists, called the transition region. It's basically just an area where we're moving from the chromosphere to the corona. And the chromosphere is kind of closer to the sun. It's like, how would I say? Like, when you breathe out and you're exhaling CO2, the CO2 that is still in your mouth until it's at your lips is still part of you, it's still in you, and then as it exits, it's still coming from you, but it's not necessarily part of you anymore, it's going into the environment. And so the transition region is like on our lips. It's like where, in the sun, it's where that ejecta is kind of like, it's going outwards enough that it's not technically the sun anymore. I mean, it is the sun, but it isn't, kind of. And so this is like 100 kilometers thick. So it's like very thin comparatively to the other regions. So yeah, and it's basically where the plasma becomes fully ionized. So it like completely breaks apart, and the density has like a major drop at this point. Okay, and then we transition to the corona. And the corona, if you've been lucky enough to see a total eclipse or an annular eclipse or a partial eclipse, the corona is basically that wispy, ethereal kind of looking like gas coming off of the sun, and it extends for like millions of kilometers. This stuff just like, it goes forever and ever and ever. It's like trails that come out from the sun, and the temperature of the corona is very hot. It's super, super hot. It's like 500,000 to a million Kelvin. It is hot. And this is also part of the coronal heating problem. People don't really know why this is, but we're trying to figure it out. And so, yeah, the density is really low. It emits UV and X-rays, and it's invisible without like solar equipment, or without total eclipse or annular eclipse. So that's the corona. It's also the source of something called the solar wind, which impacts Earth every second of every day. And the solar wind is what helps create coronas. So, sorry, not coronas. It's what helps. Oh Oh my god, why am I so... I'm so, like, just scattered today. But it's been a long day. I think it's just been a very, very long day. It's okay, though. It's what creates auroras, so the aurora borealis and borealis, which are kind of also created by Earth's magnetic field, which I will get into when we do Earth. As you find out, magnetic fields are super important. And they're what protects us from cosmic rays, radiation, UV rays, gamma rays, X-rays, all the bad, harmful stuff and the charged particles. It's the ionosphere and the magnetic sphere of Earth that protect us from that. And the speeds are like super fast in the solar wind. It's like ejecta. It goes just super fast. So, explaining the magnetosphere of the sun, we know that a magnetic field is generated by electric current, specifically moving electric current. And this is a process called the alpha omega dynamo. It's also called the solar dynamo. And this is basically because we know that the sun is made of plasma, right? And plasma conducts electricity because it has those ionized particles, those electrons, with the negative charge that are constantly moving. And the reason for this is two reasons, and I forget which part is which. Oh yeah, so the omega part is the rotation of the sun. And the sun actually rotates about its equator a little bit faster than it rotates about the poles. So the poles are 35 to 36 days, and the equator is 25 days. So the equator goes a little faster than the poles do. And this creates kind of like an imbalance of charges, and that moving charge is what helps generates, oh my god. It's what helps generate that magnetic field. And then the alpha part is convection, from that convective zone that we saw here, where that plasma that is hot heats up and then cools down, and that creates, like, from that little granule or super granule, it like makes those convection cells basically. Okay, that's all I have to say about that. And so those two combined kind of make the magnetic field so strong. And this magnetic field extends for like the entire solar system, basically. It is huge. And it also is kind of shaped really weird. I'll draw it for you, actually. It's kind of shaped like, it's like, here's the sun at the center, and it's kind of got, it looks like this. So here's the sun, and then we have the magnetic field coming out like this, and it looks like kind of like a garden sprinkler or like a flower. This is actually called the Parker spiral, which is a type of Archimedean spiral. And the Archimedean spiral is basically like, the actual equation for it is R equals V over W times theta. And it's a physics equation, but yeah, that's basically the equation of the spiral. And this is cool because it creates the solar wind, and the solar wind creates a thing called the heliosphere. And it's like a bubble around the solar system, and it's actually kind of elliptical. And then the boundary between that and something called the interstellar medium, which is what it sounds like, it's like the stuff between stars. That boundary between the heliosphere and the interstellar medium is called the heliopause. So we have the heliosphere and then the heliopause. So that's something cool. And then also we know that because we have magnetic poles, it's on a cycle. So the sun is on an 11-year magnetic cycle where basically the magnetic poles of the sun flip. And this causes a bunch of like activity, lots of prominences, lots of flares. And this, I think actually July 2025 was the maximum, I think, for we're on cycle 25. And so, yeah, this doesn't mean that it's had 25 cycles, but we just started counting, and so now we're on 25. And yeah, this is called the solar maximum and solar minimum, and I think December 2019 was the minimum, and now we're at maximum. And so we've been getting like a lot of these flares that you classify in like B, and then you can get to C, and then M, and then X. And X is like the maximum X flares. I always get excited when I see X flares because it means you can see pretty auroras sometimes. If you get these things called geomagnetic storms, which is where the flare is so strong that it sends, well, flares are caused basically by magnetic field lines interacting and shooting ejecta out, plasma, into space. And if the sun is rotating and it shoots it at Earth, it can go into Earth's magnetic field and kind of dip into the poles and create aurora, which is super cool. So yeah. What else? I need to talk about something like flares. So I have a list of terminology for you guys. So here's the terminology. And first we'll go with flare. So I kind of explained what a flare is. It's like tingling magnetic field lines, and it's like a suddening. What am I saying? I don't know why I'm so scattered today. But a flare is like a sudden brightening in the corona or chromosphere, which is super cool. And then I'm going to skip a little bit because flare and prominence are kind of related, but a prominence and a filament are a little bit different. So they're like dense, kind of coolish plasma. It's like 10,000 Kelvin for a prominence or a filament. And they're generally like loops or like spits of plasma. And the difference is that prominences are loops that we can see against space, and filaments are against the sun and are darker. And they can span like hundreds of thousands of kilometers, which is super cool. And then we have these things called Ellerman bombs. And it's also like a Severny, I don't really know how you pronounce it, mustache. And they're like intense brightenings in the lower chromosphere. And I believe the metric was like 100,000 atomic bombs. So it's like very, very bright. But it's in the lower chromosphere instead of the instead of the corona. And so, yeah. And then what else do we have? A sunspot, right. So a sunspot is like a cool region in the photosphere that suppresses convection currents. And when it suppresses convection currents, it turns really dark. And if I can show you, this is a sunspot here. It's like a dark place, and this is a prominence where we can see it from space. And this is a filament which we can see against the sun. Okay. And then what else do we have? So we can start with an ERF. An ERF is like an extreme UV brightening, basically. And then we can do plages. So a plage is like a bright chromospheric region that's over sunspots. And then a spicule, which is also called a fibril or a fibril. I think it's a fibril. They don't last very long. They last like 40 to 500 seconds long. And they're basically long jets of material. And they basically they make the filigree, which is like a pattern of these. It's like the carpet look. And then a coronal mass ejection, which I forgot and I skipped over. It's kind of like a flare, except it's like a massive flare, where like a bunch of ionized material and plasma from the sun gets ejected all at once and creates those geomagnetic storms. So it's like a giant X flare, basically. And that's what creates fun auroras. And then we have, we talked about supergranules, and the faculae is basically like the bright region around sunspots. and so I will be happy to answer any questions you drop in the comments. Thank you for listening for so long. This is not my area of expertise, and I learned a lot for this video. So yeah, but if you have any questions about radio astronomy, let me know. That's my area of interest. And I had fun learning about all this too. I didn't know that the solar dynamo was actually called the gamma alpha or the alpha gamma dynamo. I didn't know that. That was cool. So yeah, so let me know, and sorry for being so scattered. Bye, dolls.